So yeah, this is about where we left off, right? When do you end? After some fixed number of generations, maybe after some diversity level of the population hits a certain threshold, you decide to stop. Maybe after the fitness value, like the fitness of the population doesn't really change or it becomes stagnant. Maybe you end once a certain fitness value is obtained. It's up to you. Remember, do whatever the hell you want to do. It doesn't really matter that much as long as you're following the high level framework. Okay? So, TSP. Find the shortest Hamiltonian cycle in some weighted graph. Okay? All the instances that you were using for the assignment, the weights of the edges were the Euclidean distance between them, right? Because they're laid out in some Cartesian 2D coordinate system, and the weights of the edge is just how far apart they are. Yeah, black lines represent the pathway, and the red vertices represent the cities. It assumes the graph is completely connected. So that's another thing too. In your particular example, in the ones you're using for the assignment, it assumes the graph is completely connected. You can go from any vertex to any other vertex. It doesn't really matter. It's just that the edge length is however far apart they are. That's fine. And it's symmetric. Both. The weights are the same both way. Okay. Consider what parts of the GA we would need for this problem. Well, the phenotype is the Hamiltonian cycle. That's what we want. The genotype, it's an ordered collection of cities that represents some path. Okay? More simply, by assigning each city, the simplest way, in my opinion, to do this is you assign each city some integer. I believe the instances you get, they actually already have some integer assignment. Does it start at 0 or 1? Whatever, it doesn't matter, just it's whatever. Between 0 and n minus 1, where n is the number of cities. And this would make the search space every single possible combination of integers between 0 and n minus 1. So you could start with 0, 0, 0, 0, 0, 0, 0, 0, 0, n zeros, and then n minus 1 zeros and a 1, n minus 1 zeros and then a 2, and we could keep going all the way down to n minus 1, n minus 1, n minus 1, n minus 1. Right? Every possible combination of those integers. All right? That means there's a total of n to the n possible combinations. And if that's not obvious to you, that's a big number. Okay? That's a really big number. And the reason it's n to n is, let me grab a marker to make it clear. If I have n cities, how many unique integers could be in the first index? N, right? Yeah, n. And I have n indices, right? How many integers could be in the next index? N. How many in the next? N.
Isn't that assuming you can have like the same like?
Yeah, that's exactly what we're talking about here.
Oh.
This is the search space.
But like, wouldn't that be for like the same city every time?
Well, it could happen.
Oh, okay.
Right?
I bet.
So, what is this? Well, how many n's do we have? Well, that's n times n times n times n times. So that's n to the n. That's a big number. I mean, it's not going to be a big number if n is small, but usually, like, how big are the instances you're playing around with? Like, what's the smallest instance that you have? Does anyone know offhand what n is in the smaller ones?
I think
51. What's 51 to the power of 51? Let's see. That's a big number. Times 10 to the 87. All right, okay, that's a big number. 87 zeros, that's a lot. And that's only 51 cities. But, as you were just pointing out, that includes a lot of inadmissible solutions. All right? It includes a lot of solutions where, like, it includes the solution where you start at city 1, and then you go to 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 city 1, and so on and so on and so on, which is stupid. That's not a good thing. It's technically a valid solution, but it's not going to be, it defines like a Hamiltonian cycle, kind of, but not really, because it didn't hit every city. And it hit a city multiple times. So really, we want each city hit once and only once. So instead of every possible, pick a number with replacement, now it's more about a permutation. We actually, really what we want is a permutation of the cities. Start with city 0, pick the permutation 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and minus 1, and then shuffle it, shuffle it, shuffle it, shuffle it, shuffle it, shuffle it. How many possible permutations are there of the numbers 0 to n minus 1?
N factorial.
Yeah. And the reason it's n factorial, well, let's just think about this. If we have, we're starting, how many cities do we have to pick from? N. So we've used one, though. So now, how many cities do I have to pick from to go to next? Then what? Right? And then if you do that all the way out, well, that's just n factorial. Yeah?
If you're coming back to n, does it matter where you start from, really, or could you arbitrarily
Well,
start from
let's talk about that. That's a great question that we're actually going to hit in a second. I'm pretty sure we hit in a second. Now, I'm sorry to say, n factorial is still a big number, right? But, well, let's see. 51 factorial, times 10 to the 66. Okay, I don't know. But anyways. Times 10 to the 66, which is better than 87 times 10 to the 87, but that's still a big number. But it's an improvement, right? Because we've effectively eliminated from the search space quite a few possible solutions that we know won't be good. Now, when you're deciding on your representation, there's nothing saying you have to eliminate those bad ones, right? What people might say is, well, no, if you ever have a chromosome that visits the same city twice, just assign it a really bad fitness value. But then you're still including it in the possible search space. If you restrict the search space, that's good, but we have to be careful. We want to be very careful how we restrict our search space, because if we restrict it too much, we want to make sure we're not accidentally eliminating a chunk of possible valid solutions. Now here with this, it's no worries. I'm not worried about it. This constraint is a good one. We're not eliminating anything handy. Yeah. And factorial. Now, I guess I don't get to it here, but to get to your question, the problem with not fixing the starting index, all right, is if I have it such that the starting index always has to be, or the starting city always has to be 0, right? And I have 4 cities. If 0 always has to come, let's say 0 always has to come first, and I come up with 0, 1, 2, 3. That's my path, all right? If I have it where 0 doesn't need to come first, it could be any other city, but really it doesn't matter, right? Because it's still a cycle. I can point at any arbitrary vertex and be like, that was the starting one, and right? The problem there is if 0 has to come first, this is the only possible ordering of this path, if 0 had to come first. If 0 didn't have to come first, and I say I don't really care because it really doesn't matter, well then this is a valid path. Hold on. No. 2, 3, 0, 1, 3, 0, 1, 2. All of these are the exact same Hamiltonian cycle.
So it's better to fix the first one.
You eliminate n repeats of the same, well, I guess n minus 1, because one of them has to stay. Repeats of the same cycle. Now, the amount that you reduce the search space by going to a permutation rather than just some arbitrary integer encoding is way more than this. But again, every little bit helps. This does reduce the search space just a little bit more. Here's a funny thing. Here's another path. Right? That's another path. But really, it's actually the same as all the other ones. But what is it? Who can tell me what's going on there? Yeah, it's the reverse. For every one direction, there's a reverse direction. I wonder if there's a way to eliminate reverse ones. I don't know. Because if we do, then we can half the search space. Even more, which is good. I don't know. Any questions there? But yeah, good question about fixing it. What's up?
Is it necessary to loop back around to the starting thing to make it optimal, or would that sort itself out?
Well,
Like you need to go 0, 1, 2, 3, 0.
well, what I would do if I was encoding it, when I'm calculating the fitness, if I had 0, 1, 2, 3, when I calculate the fitness, I want the distance between this and this, this and this, this and this, and this and this. If I don't include that, then it's not actually going to be possibly valid because you might end up with a path that's really short. Right? Imagine here's my graph and these are all vertices. And then I go, yeah, great. But you've eliminated this. You didn't count this. So maybe there would have been a better way, I don't know. Another good question though. Whatever the encoding used is, the population usually is very simply just a collection of the coded values. The genotype, the encoding. With a permutation representation, the population would be a collection of permutations of length n. How big is it? Well, it's up to you. That's all. Fitness. Well, the phenotype is the actual Hamiltonian cycle. The genotype is an encoded Hamiltonian cycle. It's just a permutation. And the fitness is the total length of the Hamiltonian cycle. So given a chromosome, sum up the distances between the cities in order. But like we literally just said, be sure to include the distance from the last back to the first. So if here's an arbitrary example, right? If I start at 0, I go 0, 3, 5, 2, 4, 1. But I got to make sure I'm adding 1 to 0, right, like we just said. Now, I'm using the word gradient here. And what I mean by this raise your hand if you've heard this word before in the context of like machine learning. Okay, I'm going to explain this. Gradient just means kind of like a slope, okay? Right? If I've got like a ramp, that's a steep gradient, gradient, right? Right? Grading, the word grades, there's a grade. You all have grades in the course, there's like a rank. But a gradient. We like it when given to, imagine the search space. Try to envision, let's simplify it. We have a two-dimensional space in here, 2 dimensions, right? Length and width. And I want to find literally, like if you go down to the floor and you want to find the lowest part, this floor is not perfectly flat, right? There is going to be, no, let's use a different example. There exists a hottest point in this room, okay? There is a point in this room that is the hottest, okay? And if I'm looking for it, how am I going to look for it? Well, we can play that hot-cold game. Like hotter, colder, warmer, hot, you've all played that game, right? So, for those of you that haven't played that game potentially, you probably have, just maybe you call it something different. It's like if you hide my banana, right? Just, I don't know, hide it. Just put it behind your computer. So I don't see it. And I'm like, where's my banana? You could be like, warmer. Oh, right? Oh, okay. Warmer. Colder. Oh, so now I've got that. That's a gradient. I've created a gradient. Or you've created the gradient by saying hotter, colder, right? So I say colder, now, I know I'm going the wrong one. Warmer. Oh, I found my banana, right? So that game, that's the gradient, right? You're providing some information to me that tells me which direction I should go within this space. Now we generalize this to this insanely high dimensional space, TSP. I get a fitness value, and that fitness value tells me how good my solution is. If I have 2 solutions, and one is shorter, I should kind of maybe look at that shorter one, right? Because it's better, it's closer to what I want. That's a good thing, right? So it gives me a gradient. It gives me there's some directionality. A fitness value in the space gives some directionality on which way I should go. Which way how the algorithm traverses the search space. The gradient is how it kind of like guides it. Now, in these complex spaces, not all, here, let's see. These are all kind of terrible examples. So here, right? If I'm here, I'm looking for the lowest spot. If we have full view of the search space, I look and go, okay, this is the global optimum. But there's also going to be like local optimums. So this right here, in its little area, is like the best solution. If I'm here, and I take a step towards here, it'll say, well, that's good, right? Step here, that's good. And now I'm kind of stuck. Because if I take a step here, it's going to say, no, that's worse. If I take a step here, it's going to say, no, that's even worse, right? So a gradient is good for guiding us, but just following a gradient isn't always great. If you have a nice convex or concave search space, yeah, just follow the gradient, boom, you'll find it. Do a simple hill climbing algorithm, or hill descending algorithm, I guess, depending on which way you're going. But a lot of the problems we're dealing with aren't this nice. We're not using evolutionary computation for problems like this. We're using them for problems that are probably a lot worse than this too, but more like that. So A gradient is important to have. It guides the search, but it's not the end-all be-all. You have to make sure your algorithm has the ability to kind of knock itself out of local minima or maximas depending on maximizing or minimizing problems. Does that make sense? So a gradient is like something guiding me in the direction that I probably, hopefully, really want to go. So that's that point. Not all improvements will necessarily be a step towards the optimal solution, though. So which variation operators are used is going to depend. It depends on a lot of things. We talked about some variation operators before, crossover, mutation. But if you've been working on the first assignment and you decided to use that permutation representation, those crossover mutations aren't going to work very well. Because first of all, a bit flip doesn't even really make sense anymore if you've got a permutation. What does that even mean? It's not possible. And then a single point crossover, we got a problem. So yeah, here, let's just go through this because I'm sure I've got the examples here. For the permutation representation, a single point mutation will not work well. So a bit flip mutation, there's a variation of that, like another one, like a single point mutation, where basically you pick an arbitrary index and you just change its value to something else from the possible values. If you were to do that and you have this permutation, and I pick the seeded index 3, 0, 1, 2, 3, which is 4, and I replace it with any other value that's not a 4, I'm going to break the permutation. It's not going to be a permutation anymore. You understand? If I replace the 4, someone name a number between 0 and 6 that I can replace with 4. 5. 5's already there. And then we didn't go to 4. So we're in trouble. So that's no good. So maybe we could do something, another really simple one, a swap mutation. Pick two cities and just exchange them, swap them. You're not adding or removing any city, you're just changing where they exist in the cycle. There, mutation, we've got a safe mutation for permutation, great. Crossover, if I have this permutation and its reverse, if I pick any index to do the 1 point crossover, except index 0, because index 0 would change nothing, it would just effectively swap the chromosomes. If I pick any index there and do the crossover, I'm going to have a big issue. Let's do it here real quick. 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4. I'm going to be lazy and do that. And then I've got 4, 3, 2, 1, 0. Someone pick an index. Anyone that's not 0. Pick a better one than 1. 2. Great. 0, 1, 2. Okay. So we're going to cross over here. Let's say that's included in the crossover. So the result of this is 0, 1, 2, 1, 0, and then 4, 3, 2, 3, 4. Well, those aren't permutations anymore. I go from city 0 to 1 to 2 to 1 to 0. I skipped 3 and 4. So a 1 point crossover, it ain't going to work for a permutation representation. Any questions so far? There are more complex crossovers. First of all, you can do whatever the hell you want to do, as long as it works. But there are some more complex crossovers like partially mapped crossover or ordered crossover. These are like well-defined crossovers that would work in a situation like this. Selection. There are a lot of possible ways we could do selection. I like tournament selection. It's easy and it works really well. And what I like about it is it gives me that K. It allows me to tinker with how big the tournament size is. You know, I can increase K to increase selection pressure. I can decrease K to reduce selection pressure. I like that. If we're doing a generational algorithm, like a generational GA, we also need another selection. Or no, we don't. We only need one selection. If we're doing steady state, we need another selection for, well, who's going to get replaced in the population. And you can do that however the hell you want, based on age, like the number of iterations it's existed for, maybe replace ones with low fitness, randomly replace. It's up to you. Initialization and termination, well, all right. Randomly generate for both encodings, randomly generate the chromosomes would work for both encodings. Well, yeah, I guess, yeah, that's true. Randomly generate chromosomes, you know, Python random library will help you there. Termination, run for some fixed predetermined number of generations that I just arbitrarily choose. There. There's my initialization and my termination. But once I've made the decisions, I've got my GA. I've got my general implementation of what I want to do. Any questions? So, typical settings. Well, there are a lot of hyperparameters to set. By the way, did I explain to this class yet why they're called hyperparameters? Did I make that joke to you? You think, I'll say it again just to be safe. So typically you call these things parameters. And if you were going through the text for the course, they'd be called parameters. But what happened a couple years back is, so the deep learning people, they wanted to be a little bit more in line with like the statistics, because there's a lot of similarity between the machine learning and the statistics. And so like in like a regression analysis, you know, regression is basically find a straight line. And you remember drawing straight lines in grade 9, right? Y equals mx plus b, right? What's the slope? Well, when you're doing like regression, you want to find like, well, what is that slope? Okay, you want to find that. And when you find it, the statistics and the basic algebra that goes into the regression analysis, it's called, like tuning that m would be like tuning that parameter. Like the algorithm is looking to find that value for the regression. That's called the parameter. So the machine learning people, like the deep learning people, the neural network people said, well, okay, so we're going to call the weights in our graph the parameters. And then people are like, well, hold on a moment. But then what do we call all those things that we tune before we hit run? You know, if I hit run on my algorithm and I say the weights are what the algorithm is learning, and we're calling those weights parameters, then what do I call what I've been calling parameters? What do I call the parameters that I tune before I hit run, like how big my network is and how many nodes there are and all those sorts of things? What do I call those? And then they came up with the genius idea of hyperparameter, which has an entirely different meaning in mathematics. So in an attempt to align themselves better with mathematics, they've just made things worse. And as a consequence, this has started to permeate into other fields of machine learning where everyone else is like, fine, fuck it, we'll call them hyperparameters now. So if I use the word parameter and hyperparameter and I interchange them, I don't really mean to, but I am referring to the same thing. So these hyperparameters are things like how many generations, what's the crossover rate, what's the mutation rate, what's the population size, etc. So what are typical settings? If I'm doing TSP, what are some typical settings? Well, number of generations. This one's really hard to give you like a rule of thumb for because honestly it's however long it needs to be. If you hit run and you look at your plot of how that learning curve looks, if you're doing TSP, let me draw again. If your graph looks like this, right? Now it's a bad one because it does hit the the x-axis. It looks like this, and this is generations, and this is fitness, and we're minimizing fitness, right? Can you even see that? Is it hidden by the computer for half of you?
A little bit, yeah.
Maybe this will help a little bit. Maybe.
There you go.
If you see that, I would go, well, you should probably let it run a little longer because it's not done. So increase the number of generations. And if you do that and your curve starts to look like this, well, yeah, okay, now it's starting to converge. It doesn't really look like it's improving. Yeah, that's probably a good number of generations. Maybe I'd let it run a little bit longer, but whatever. So the number of generations to use, that's going to depend on on the problem you have, and you just let it run for however how long it needs to run. Is it still improving when it stopped? Then you need to let it run a little longer. Usually when I'm doing this, what I will do is I'll start with some values, maybe 1,000. If it doesn't look long enough, I usually operate in orders of magnitude. If 1,000 didn't work, try 10,000. If 10,000 didn't work, try 100,000. If 100,000 wasn't enough, try a million. I usually just work like that. If you start like doubling, I don't know. I would recommend working in orders of magnitude. Just add a 0. But it's up to you. Similarly with crossover. Similarly with population size. How big is it? Well, depends. Now the tricky thing with all these values though is the decision for one value will affect the decision for another value. These things are so interconnected in how they play that when you change one, you might need to change the other a little bit. Population size, maybe start at 10, try 100, try 1,000, and so on and so on and so on. Crossover rate, I don't know, start around 80%. Mutations, 10%. You know, the initial settings you hit, you'll get fine results, but it's always important that like after you hit run, you see the results, you go back, you kind of tweak those settings, those hyperparameters to different values, you hit run again, and you see, did it improve or not? Now, these, the right way, when you're doing the tuning, when you hit run once, there's a lot of randomness involved. Every time you hit run, you're going to get a little bit different results. So really, it's not great to make a decision on your tuning based on a single run. But for early preliminary testing, if you hit run once and you see, okay, the population didn't really converge yet, add more increase the generation. If it seemed to converge really early, try increasing crossover or mutation, see what happens. Just look for big general trends, which you were kind of doing with the bit string optimizing problem, but that was a very simple problem. Next, we're going to talk about N queens. That's less simple, so you get a chance to play around a little bit more, and so you'll get a feel for how tinkering affects it. But again, it's really not safe to make a big sweeping conclusion like, oh, it was better to have a crossover rate of 85 because I got a better run, I got better results on that one run I did. Wow, one run isn't enough to make a conclusion, but it's enough for your quick and dirty tuning. And I will also say, when you're tinkering with crossover rate, don't go crazy. Try 81, try 85. If 85 was better, good. Don't go to okay, what about 82 and a half? 82.5172%. No, don't do that. You're wasting your time, right? Don't look at that level of detail. Tournament size, maybe 2 to 5, but this really depends on the population size. If the population is really big, as the population increases in size, your tournament, if I had, let me put it this way. If I had, remember the word selection pressure. Selection pressure is a word to mean the highly fit individuals are very likely to make it to the next generation. A high selection pressure situation is that. You're very likely to make it to the next generation. If I had a population of 10, and I have a tournament size of 2, I randomly pick 2 chromosomes, and I take the better of the 2, right? I've got like a 20% chance to pick the best one to make it to the next generation. If I have a population size of 100 and I pick 2, I have a 2% chance to pick the best one to make it to the next generation. But at the same time, I'm also going to be selecting 10 times the number of things to make it to the next generation. So maybe it kind of balances itself out. The point here is, if you increase the population size, you might need to tinker with how big your tournament size is. These things are so insanely interconnected that it's difficult to really, you really can't tune these things in isolation. You can try, I certainly try, but in reality, they're all so connected that you just really can't. When you change one, all the other ones change as well. So although some specific values are mentioned above, all these settings, you really need to determine these settings by doing some trial runs. You got to start somewhere, you hit run. How good was it? You tweak them a little bit, hit run again. Was it better? Good. Was it worse? Okay, well now I know, go back to what they were. You really can't just pick them and go. Now these are all what we call the numerical parameters. These are the parameters, see here, look, I'm calling them parameters instead of hyperparameters. Oops. These are the numerical parameters. Now they don't necessarily they don't necessarily have numbers associated with them, but they're like the very low level things, like what's the crossover rate? These are very low level. There's also what we call the symbolic parameters, or what people try to call symbolic parameters. These are really what make up your GA. So the symbolic parameter would be like, what was your crossover that you used? What was the mutation that you used? What selection operation did you use? Because remember, a GA, or evolutionary computation, is that high-level framework. As long as you're following that high-level framework, you're good to go. How exactly you do selection, it's up to you. But the way you're doing selection, that would be the symbolic parameter. And sometimes your choice of symbolic parameter comes with the numerical parameter. For example, tournament selection. If I choose to do tournament selection, well, now I have to pick the tournament size. One of the criticisms people have of evolutionary computation is, there's a lot of things that you can tweak. I think people make that criticism if they get stuck in the mindset of, well, now I need to find the optimal configuration of my parameters to find the best possible result. Which, okay, there's nothing incorrect about that statement, but you really don't need to find the optimal. That's kind of that's a foolish game. Don't try to do that, right? You just kind of play around until you get results that you're happy with, and then you carry on. Because remember, I know we're computer scientists and we love to geek out about our algorithms, how complex they are, and the best possible solution we can get. But in practice, we would be using these algorithms to solve very complex, real-world problems where people just need a good solution. So if you come up with a good solution, they're going to be happy. If someone comes along later with a better solution, they're going to be happy. But don't waste everyone's time by being like, what if it's a crossover rate of 79.7142122227? That's foolish. Don't do that. You're wasting your time. Typical behavior, well, when you have a randomly generated population, which you don't have to have it randomly generated. Maybe what you do is you half randomly generate, and then you half come up with some solutions that you know are already kind of good based on some other heuristic. You throw them into the population as well, and then you hit go. That could work, but that could also really get your algorithm stuck in a local optimum, which is a problem. So there's again, do whatever the hell you want. But if you've got this randomly generated one, here's a one-dimensional search space. It's a line, right? The one dimension, these points can move left and right. and the height is their fitness value. Each point on there is a chromosome. All the points is the population. And so each of those chromosomes is going to have a fitness value that's represented on the y-axis. So that's what you're going to have usually when you start, something like that. As the algorithm starts to go, it's going to start looking a little bit more like that middle one there. They start to cluster a little bit around what's good. And then later on in the algorithm search, you're going to have something like this, where maybe you've got some close to the local optimum, some to the global optimum, etc. So that's usually what you expect to happen with your evolutionary algorithms in your search spaces. Now, this is a one-dimensional search space, so this is very simple. If you're doing something like TSP, you have hilariously large dimensional search spaces. So don't try to visualize it, but just use this as the analog to what's happening, right? The points are going to kind of start to converge on the parts of the search space that are better than others. And then here's an example learning curve. Best value in the population of fitness. Now this is obviously not for TSP, because TSP is a minimization problem. This would be for a maximization problem. Higher fitness is better. This is usually what you see. If I saw this curve, like if someone submitted this curve to me for an assignment, I would say, probably should have let it run a little longer, because it's still going up, right? But it's clearly not rapidly growing like this. The early stages of evolution, you're going to have rapid increases. Mid stages, a little bit. And near the end, it starts to become more and more flat. That's what you should typically see. Not always, but usually. And then a final note. When trying to solve a problem, you don't want to use evolutionary computation. You don't use evolutionary computation unless you have to. It's a last-ditch effort. It's the same thing with like deep learning. They're in the same class of type of algorithm, computational intelligence. You don't want to use these algorithms if you don't have to. But there's some problems out there where we go, fuck, I don't know what else to do. And you throw these behemoth algorithms at them and you finally get results. We don't want to use this stuff because it's computationally expensive. They're notorious for overfitting. It's hard to understand why the hell the algorithm came up with the solution it did. And it's not even going to find the best solution to a problem. But remember, when we resort to these things, often finding the best solution to a problem is not even our goal. It's to find a good solution to the problem. Yeah, you had a question?
What's overfitting mean?
Overfit means, now this really depends on the context, and this is more of like the applicability of the word overfitting isn't great for your general evolutionary algorithm, but depending on how you're using evolutionary computation, it could work. Overfitting would be, if I'm doing machine learning, like a classic example. Raise your hand if you've done machine learning before. Okay, a couple of people here. So, one of the classic examples is the iris data set. Are you familiar with that, the iris one? Okay. Given dimensions of flower petal widths and heights, lengths and widths, and sepal lengths and widths, can you classify their iris flowers? Can you classify which specific of the three breeds? I don't know, what's the word? Species? I don't know if that, whatever. Three types of irises they are, okay? Based on these values. So what you will do is you give a chunk of data to your algorithm. And your algorithm looks at the data and goes, okay, so all of the ones with lengths and widths around here are this class. All the ones with lengths and widths around here are this class. And all the ones around here are that class, all right? But the problem, you know what, this might be better shown. Nature is messy. First and foremost, nature is messy. If I have a space like this, let's say this is a really simple length, width, only a two-dimensional problem. If I have and let's say there's two classes. right? And your algorithm comes along, and your algorithm looks at this and it goes, okay, I can draw the boundary. The boundary looks like this. Right? Right? Great. And then a new piece of data comes along and it goes right here. Right? And maybe it's like right in this point. So it's like, oh, okay, well clearly that's going to be an O because it's on this side of the line. But it's like, well, I mean, this algorithm worked really hard to fit that line. Everything along here is kind of like, it could go either way. It's hard to really say. I don't really have a lot of data to generalize that well. So when you have new points along this edge, right, if I have an X here, maybe it should have gone like this. So overfitting would be when you see something like this. Hopefully that helped. Did that kind of help for those that were unfamiliar with that phrase? For those that know machine learning, does that kind of make sense to you? A little bit, yeah. All right, we'll wrap up here.